let's go ahead and do those stress calculations then. The maximum shear stress in the steel is going to be equal to the torque in the steel. So that's going to be 2.276, and that is kilonewton meters. So there's going to be a 10 to the third if we think of newtons as going to be our meters. Then we've got the radius, the rho value, the outer value is 54 divided by 2. So that's going to be 0.054. That's the diameter of the steel divided by 2. So notice we're choosing newtons and meters for our units for this particular problem. And then the value of J is the one that we computed earlier, although we canceled out the pi over 32. That's going to be pi over 32 times 0.054 raised to the fourth. So this is the J of the steel section when we do it like that. And we do all that and we find that tau in the steel is equal to 73.6 MPa, 10 to the sixth. So that is our maximum stress that we've got inside of the steel section. The shear stress in the aluminum is going to be its torque. So that's going to be 1.724. And again, just like we did up here, we have to do times 10 to the third to get it from kilonewton meters to newton meters. And then we have its outer max is going to be half of the outer radius to that shell. So that's going to be 0.072 divided by 2. And then we have its J, a little bit of a nuisance, but it's not bad, pi over 32. Same value that we had in the calculation when we did the theta. So that's going to be 0.072, pardon me, 0.72 to the fourth minus 0.054 to the fourth. And our units are all set up. And when we get that, then we find that the tau max in the aluminum, and again, the max is kind of implied when we write these things, and that's going to be 34.4 MPa, like so. Then what about theta? Theta, we can use either one. Theta of the aluminum is theta in the steel. So we can use either expression. And let me take you back. I guess I can't because that was in part C. So we can't quite go back. But if you look at those two problems and I ask you which one is easier, well, in my opinion, unless you've pre-calculated J, it would be the J of the steel because that's only one value. It's pi over 32 times 0.054 to the fourth. You don't have to subtract anything off. So you could say, arguably, I suppose, that that is going to be the easier calculation unless you've already stored it and you've already done that calculation. But in any event, I'll go ahead and pick that value. So the theta in the steel is going to be its value of torque, that's 2276, times the length, 25 meters, divided by pi over 32 times 0.054 to the fourth. And then we have its value of G, 77 times 10 to the ninth. And we get a value, and I'm going to say dot, 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 that's going to come out in radians. And we're going to do a calculation. It's going to be equal to 50.7 degrees. That's huge. But remember that that's over a length of 25 meters. So twist per length would be what? About 2 degrees. 2 degrees per meter. And that's small. So that's okay. That's probably in the realm of small angles that we've been talking about. It's so large in this one just because the length is going to be so long. Okay, so that's how we calculate all of those parameters. That's a very common type of calculation. So this is a classic statically indeterminate torsion problem. There's one other thing, though, that we want to kind of expound upon. And I want you to notice something. The max shear stress in the steel, 73.6. Max shear stress in the aluminum, 34.4. So I want to redraw that down here. So the plot of tau over the radius of the section. What does it look like? Let me blow this up. There's our aluminum shell. There is our steel core. And it looks something like this. So I'm going to just kind of rough hand this value in. So we have 73.6 MPa as the maximum in the steel. So I'm going to put an arrow up about this high. Now we know that in that segment it's linear, so it looks like this. Like so. That's the T rho over J, where J is just the value of J of the steel section. And what happens is we get a 73.6. But then notice what happens in the aluminum. It's half the value, actually less than half. It's down here. That's tau max in the aluminum shell. That's 34.4, both MPa. MPa. And what does that look like? Well, that has a T rho over J, where it's the rho of the outer section of the shell. So it's going to look like this, like so. So we're going to have a value there, right? That value here and here. So notice the stress distribution. It is no longer linear. It is piecewise linear. So this is very important for us. The plot of tau is piecewise. Linear, and there is a drop in the shear stress at the interface. There is a drop in tau at the interface. And why is that? Well, if you go back to our kinematic model, so remember, our kinematics said that gamma is linear. So if gamma is linear, that means that if I look over like so, it's going to look like this. So the angle looks something like this. So we have a value of a plot of gamma, and here's our value of rho, and it's going to be a straight line like this. There's our interface. But now what happens at the interface? Here in this section, I have a big G. I have a big shear modulus. It was 77. Here in the other segment, I have a small g. So now when I calculate tau is equal to G gamma, the mismatch in the shear modulus causes a mismatch in tau. Let's write that out. A mismatch, or the jump if you prefer, a mismatch in G causes a mismatch in tau. And by mismatch, we mean that there's going to be a jump. So what we've seen is, if we have two materials, let's call it 1 and 2, we have seen already, let's draw this off to the side, what happens when G2 is going to be less than G1. That's the one that we just did. What happens to the plot of the shear stress? I'm going to redraw it like this and like this. What happens is, here's what we want to do. We want to draw a radial line, and then we're going to draw a smaller value of the arrow. So there is our linear distribution in the outer section. But then G1 is bigger, so all of a sudden there's a jump up like this. And we connect that as a linear distribution. Notice that goes through the origin, this goes through the origin. So through the origin, both do. So that's what the plot looks like then when the inner is greater than the outer. So we would sketch like this, and then it drops. So going from here to the other material, there is a down drop. And the magnification factor would be the g of the 1 divided by the g of the 2. So that's a scale factor that we have. So factor of g of 2 divided by g of 1. What happens then when the g2 is greater than g1? What happens in that case? Well, we do the same thing. We draw the radial line. Go ahead and draw the linear distribution like this. So it's got a linear distribution inside of the core. But then there's a jump because of the jump in G, and then draw another dashed line like this, draw a linear distribution, and now it skyrockets at the interface like so. So now there's an upward jump. So here, downward jump. For this sort of material, there is an upward jump. And it's all because of the G mismatch. And this is a very important factor. It's a subtle point, and I want you to make sure you understand it. So now if we had to draw stress distributions, what would it look like? If it's solid, it looks like this. Solid and homogeneous. In other words, one material. Hollow and homogeneous. It stops right there. There's no stress inside of the air. It looks something like this. So this is hollow and homogeneous. And then we've done the other two. So we've got the G2 is greater than G1, and we have the G2 is less than G1. So there are really 4 plots. So I want you, this is my closing admonition, know them. Make sure you understand those plots, and we'll probably do a numerical example that'll make that gel. But until then, we're done, man. See you next time.